Hi everyone, in this video we are going to be reviewing the last semester's 2271 midterm paper. Okay, so a few of you had asked to go through the discussion for these questions, so that is why I'm making this video. Okay, so let's go on to this first question over here. We are given the following code, all right, and we are asked to answer these questions with reference to the appendix. Okay, so what was given to the students in the appendix was the information on the port PCR register as well as the SIM SCGC5 register. All right. So with reference to the code above, what is the objective of line 2? Okay, so let's look at line 2 over here. So in line 2, what we are doing is we are writing to the port D PCR register using this port alpha macro, and the value we are passing in is 0x0a or with 0x01. Okay, so let's look at this value first. Okay, so if you look at this value, basically it is a is 1010, and we do a OR operation with 0001. So the answer would be 1011. Okay, so that is the value we are passing into the port alpha macro over here. And what does this do? It shifts the x value by this port alpha shift amount, which is 16 bits. All right, and we are then doing a mask, okay, based on this particular mask value, 0xf0000. All right, so basically what we are doing is we are taking this value, all right, 1011, and we are going to shift it to the left of left by 16 bits. All right, and then we are going to do a OR operation with whatever data that is already there in the bit positions of 16, 17, 18, and 19. All right. Basically, this lower 4 hex represents the bit positions from 0 all the way to 15. All right, and this F represents the bit position from 16 all the way to 19. All right, so if you look at the port PCR register, okay, 16 to 19 is referring to the IRQC bit locations. Okay, now if you look at the IRQC definition, okay, for the bits that you can write to it, we are writing a value of 1011, and that means we are going to interrupt on either edge. Okay, we're going to interrupt on either edge. Okay, so basically what line 2 is doing is we are going to enable the interrupt, okay, on both the rising and falling edge of port D pin 6. All right, so that is the answer for question 1. All right, so let's go on to question 2. So in question 2, they asked you asked the objective of line 3. Okay, so let's look at line 3 over here. So in line 3, what we are doing is we are doing again a write to the port D PCR register, but this time we are using the macro port beta with a value of complement 0xFE. Now what is 0xFE? This 0xFE is basically 1111 1110, correct? And if I do a complement of it, what I get is 00000001. All right, and I'm going to use the macro port beta. So in port beta, what I do is this value I'm going to shift left by this port beta shift, which is 8 bits. All right, and I'm going to do a mask with this value here, 0x700. All right, so basically what will happen is when I shift left by 8 bits, all right, it will come to bit position 8, 9, 10, 11, correct? So in the 32-bit sort of register, it will come to this position 8, 9, 10, 11. But since I only mask with 0x700, 0x7 is basically 111, 0111. So I'm only interested in the bit positions 8, 9, and 10. Alright, so the bit positions 8, 9, and 10 in the PCR register, right, refer to the functionality of the multiplexing. Okay, So if you look at the multiplexing, all right, uh, the value of 001, which I'm writing to this bit positions, refers to the alternative 1 function, which is the GPIO function. Okay, so basically what I'm doing in question 2 is to enable the GPIO functionality for port D pin 6. So only statement 3 is correct. Okay, so I'm not doing anything with the internal pull-up resistor or the slew rate. Alright, so though those functionalities are also in the PCR register. Okay, so if you look here, there is a slew rate and the pull-up, pull select, enable, and so on. All right, but we are not doing anything to those particular bits over here. All right, we only focus on the multiplexing configuration in line 3. All right, so only statement 3 is correct. Okay, so let's look at question 3 over here. The following signal is generated by the switch connected to port D pin 6 whenever it is pressed and released. Alright, so whenever it's pressed and released, this signal is generated. When it is pressed, a negative transition is generated. So this is when I press it, and this is when I release it. Okay, so once I release, it generates a positive transition. Alright, so how many interrupt requests will be registered by the microcontroller based on the current configuration? Okay, so if you get the question 1 correct, alright, which is to basically say that we are going to interrupt on both rising and falling edge, alright, you can answer this question easily. Alright, so basically you every time you press and release, you have two different triggers for the interrupt. Correct, so 2 interrupt requests will be registered by the system. Okay, so the answer here for question 3 here is B. Okay, 2 interrupt requests will be registered by the microcontroller. Okay, for question 4, port D is mapped to IRQ31. The priority is configured in IPR7. Alright, so we are also told that no other interrupts are configured in the system. So what is the 32-bit value in the IPR register based on the given code? Okay, so what we need to first understand is we are only going to configure IRQ31, which is here. Okay, so this is the upper 2 bits of this 8-bit block. Okay, so you have to remember that each IPR register, alright, the total of 8 IPR registers, and within each IPR register, you can configure the priority for 4 different interrupts, but the configuration is only in the upper 2 bits of each 8-bit block. Okay, so there are 4 8-bit blocks, okay, and only in the upper 2 bits you configure the priority level for a particular interrupt source. So in this case, we know that we are dealing with IRQ31. Alright, so the value that we are going to write to is in the upper 2 bits of this 32-bit register. Okay, based on this 8-bit block over here. Now the next thing is, what is the actual priority of that port D is configured for? Okay, so we need to look back at the code over here. So in the code, we can see that the priority level is set to 1. Okay, so if the priority level is set to 1, okay, that means a value of 0, 1 appears here. Alright, and the rest of the bits will be default, holding a default value of 0. Okay, so as far as this 8-bit value is concerned, okay, this 8-bit value is going to have a hexadecimal value of 0x40. Okay, and since no other interrupts are configured in the system, everything else will have the value of 0 by default. Okay, so the value, alright, that is written to this IPR register is this. Okay, 0x40000000. Okay, so that is how you answer this question over here. Now question 5 is related to this, where we are asking you that if I were to directly write to this IPR7 register, which would be the correct code that configures the priority. Okay, so if you look at the bit pattern here, everything else is 0 except for this 1 over here. So this 1 over here, okay, that is in bit position 30. Okay, it's bit 30. So basically, as long as I take a value of 1 and I shift it to the left by 30 bit positions, then that basically will give me the same result as the or the result that I want in order to configure the port D priority at the correct value of 1. Okay, so that's why the answer for question 5 here is C. Okay, so let's go on to question 6. So question 6 is again tying back to the signal that we saw just now. All right, so we saw that what we want is we want to generate a signal that looks like this. All right, so this is when we press, okay, and this is when we release. Okay, so the important thing you understand is what is the default value. The default value is a high, correct? When I press, it goes low. Okay, so if I look at this 4 different switch configurations, in option A, the default value, okay, of port D is tied to ground. All right, so this cannot be an option. Okay, similarly in option D, the default value of port D is again tied to ground to a resistor. So this also cannot be the option. All right, only in options B and option C, the default value is tied high. Okay, so it's either option B or option C. Now the next thing I must check is when I press the switch, does it make a transition to the low over here? All right, so if I look at option B, all right, so you can see that by default it is a high. When I close this switch, I create a short circuit path to ground, correct? So it will go low. When I release the switch, it will go back high again. So this is the answer. All right, so let's just look at option C. So in option C, it is high, all right, but when I close the switch, it is still high, correct? It's still high because the short circuit part to VCC is still there. Okay, so even though I close the switch, the voltage reading from this particular point here will still be high. Okay, so closing and opening the switch doesn't actually change the voltage level seen at the port D pin 6. Okay, so it is not option C. So the correct answer here is option B. Okay, so let's go on to question 7. So in question 7, we are told we are reviewing the periodic interrupt timer module. All right, so let's examine these statements. So in statement 1, the timer start value can be changed at any time. All right, so that is true. All right, so anytime you can change the timer start value so that when it reloads again, it will start from a new value. All right, next is statement 2. We can configure interrupts to be triggered whenever a timer counts down to 0. Yes, it is true. Statement 3. We can configure interrupts to be triggered whenever the timer counts up to a particular specific value. All right, so this is not true. All right, because it only triggers when you count down. All right, and then you overflow. All right, so it does not trigger when you count up. So only statements 1 and 2 are true. So the option here is B. Okay, let's go on to question 8. The earlier program is updated with the code to allow the PIT module to generate interrupts. The following sequence takes place. Alright, so when we say the earlier program, so we are referring to the code already given to us where we have the switch already configured, alright, to generate interrupts. Okay, so the following sequence takes place. The main code is running, alright, and the push button is pressed. And immediately after the push button is pressed, the PIT module generates an interrupt. Alright, so what are the possible scenarios? Okay, so the first statement, the moment the PIT generates an interrupt, the code will immediately jump to the IRQ handler for the PIT module. Is this a possible option? Yes, it is a possible option, correct, if the PIT module was configured to have a higher priority than the push button. Okay, the push button IRQ handler will complete first and then will execute the PIT IRQ handler. Yes, this is also possible, correct, if the both of them have the same priority or the PIT module has a lower priority. Alright, so that is also a possible option. Now, the third statement, the PIT module's interrupt request can be programmed so that it's ignored and the interrupt is never serviced. This is also a possible option, alright, because alright, you can clear pending IRQ. Alright, so anytime you can clear a pending IRQ from another interrupt as well. Alright, so it is possible that I'm in the push button IRQ Alright, and then I can execute a code to clear any interrupt that was actually generated by the PIT module while I was in the push button IRQ. Alright, so all three statements are possible. Okay, so the correct answer here is E. Okay, so let's go on to question 9. Which of the following statements is true for a volatile global variable? Okay, so when we say global, firstly, you must know that you can access it from any part of the code. That means any function, any interrupt can access it. And when you say it's volatile, we must understand the idea is that every time you want to uh, you are reading from this variable in the code, you will fetch a new copy, okay, from the memory to make sure it is the latest updated value. All right, so as long as you have these two understanding clear, then this question is easy. So let's look at statement 1. Whenever the data is accessed in the code, you will use the last fetch data that is stored in the internal registers of the processor. All right, so this is not true. All right, because as long as you say it's volatile, you will not use the stored value. You will always fetch a new copy of the value. All right, so statement 1 is not true. Whenever the data is accessed in code, a new copy of the data is always fetched from memory. All right, this is what we just discussed. And since it's global, it can be accessed by a task and an interrupt. Okay, so only statements 2 and 3 are true. Okay, so that is 9C. Okay, in question 10, the UR2 module in the Cortex M0 Plus is configured to operate in interrupt mode for both transmit and receive. Which of the following statements is true? Okay, there are two separate IRQ handlers for the transmit and receive interrupts. So this is not true. All right. There is only a single IRQ handler. Okay, within the IRQ handler, you must check the flags to decide which is the whether transmit or the receive generated the interrupt request. Okay, so there's only one IRQ handler. That is what we just discussed, and there are two separate flags. Okay, for us to differentiate and know who is the one who triggered the interrupt. So only S2 and S3 are true. So the correct answer here is B. Okay, so the remaining questions are based on the context of the RTX RTOS. All right. So let's look at question 11. A task T1 that is running gets switched to the ready state. Which of the following could be the cause? All right. So let's understand. So a task is currently running, and then it gets switched out to the ready state. Okay. So from the run state, I'm getting switched to the ready state. Option A, another task acquired a resource that was being held by T1. Alright, so this cannot be, because if task 1 is running, then another task suddenly cannot just acquire a resource. Correct? Only a task that is running can acquire a resource. So if task 1 is currently running, no other task can suddenly acquire a resource that is being held by T1 while it was running. Right? So that cannot be a possible scenario. T1 attempted to acquire a resource and was successful. If it attempts to acquire a resource and it is successful, it will carry on running. All right, there's no reason to go to any other state. Okay, so it will carry on running. So this is also not true. T1 attempted to acquire a resource that is currently unavailable. Okay, so if I try to acquire a resource that is currently unavailable, then I'll transition to the block state. Okay, I'll transition to the block state, not to the ready state. So this is also not true. T1 chose to call OS delay 1 in its code to voluntarily give up the CPU. Okay, so from what we have seen from the documentation, we know that OS delay 1 actually, OS delay basically puts your current task in a block state. Right, so it doesn't go to a ready state, it goes to a block state. So this is also not true. So none of the above statements are valid. So 11 is E. Okay, so let's go on to question 12. A task T1 that is running gets switched to a block state. All right, so I'm in the running state right now, and then I transition to the block state. Okay, so which of the following statements is true? Task T1 is preempted by a higher priority task. Okay, so if I'm running and I'm preempted by a higher priority task, okay, then I will be transitioned to the ready state. Okay, so always remember, if you are running means you have all the resources, correct? But if somebody more important comes along, a higher priority task comes along, then that task will be switched over to the run while you transition to the ready, correct, and wait for your turn. So this is not true. Task 1 attempted to acquire a resource but was unable to get it. Alright, so this is what we discussed in the earlier question. So whenever you attempt to acquire a resource but you're unable to get it, then you go to a block state. Alright, so that is B. So B is the correct statement. Now let's look at statement C. T1 was allocated a resource that it was waiting for. Alright, so if you're waiting for something, alright, then you should be in the block state. Alright, and when that resource is allocated to you, you will transition to the ready state. Alright, and then the scheduler will transition you to the run state. Okay, so if you are waiting for something, alright, then you will not be in the running state, you will be in the block state. You're waiting for a resource. Alright, so C is not true. Task 1 was preempted by another task with the same priority as T1. Okay, so this is basically like what we saw in the lab, where you have multiple tasks with the same priority. So the default behavior of RTOS is to switch through a round robin schedule, okay, between those tasks. All right, but when that switching happens, you are transitioning between run and ready. All right, you don't go to a block. Okay, because rightfully you have everything you need to run. Okay, it's just that the scheduler is trying to do some time slicing to give every task in the same priority equal amount of CPU time. All right, so you transition between run and ready. So this is not true. All right, so option B and D are both true. No, so the correct answer is B, 12B. Okay, a task is currently in the running state with all the required resources. The scheduler will still perform a context switch after some time to ensure that other equal priority tasks have a chance to execute. Alright, so this is basically what we saw just now when we discussed about the round robin behavior. Alright, so as long as you have multiple tasks which are ready in the same priority level, then the OS will actually do a context switching amongst them, alright, to ensure that every task with equal priority has a chance to execute. Okay, so the answer here is A, true. Okay, so the last question here, we are shown two threads. Okay, LED red thread, LED green thread. Okay, and the rest of them are quite basically a standard code that we've been seeing in our labs and example in the lecture slides. So let's look at the following statements. The first one, the init GPIO function is necessary to ensure that the GPIO pins used by the RTOS scheduler are correctly initialized. Okay, so firstly, anything that the RTOS needs, okay, from the system will be handled by the OS kernel initialize function. Okay, so it does not need any GPIO pins. All right, so from what we discussed, it needs memory, it needs timer, blocks, and so on. All right, so those are for its background processing and keeping track of the events that it's handling. All right, but other than that, it does not require anything much. All right, but whatever it needs, it is handled by the OS kernel initialize function. All right, so you do not need to call any other function, all right, to set aside anything for the RTOS in particular. All right, the OS kernel initialize function does everything for us. All right, so this is not true. The scheduler will randomly decide which of the two threads will run first. All right, so this again is not true because whichever thread was created first will be the first to join the ready queue. So since LED red thread was created first, that will be the first in the queue. Okay, then followed by the green thread. All right, so whoever was created first will be the first in the queue. All right, and the last statement, the moment we complete OS kernel initialize function, we have switched over to the RTOS multi-threaded environment. Not yet. All right, we need to call OS kernel start. All right, so until we call OS kernel start, we are still in the single threaded environment. Only when we call OS kernel start, we are transitioning over to the multi-threaded environment. So statement 3 is also not true. Okay, so all the above statements are false. So the correct answer here is E. Alright, so basically that's about it. Alright, so I hope that this video has given you a good overview on the questions, alright, that we had that the students had for the last midterm. Alright, so if you still have any doubts, feel free to discuss them with your TA, or you can ask me as well. Alright, thank you. and I'll see you in class. Bye.